Okay, so this is the next shape we'll be working on, finding the first moments so that we can find the location of the centroid. So we've got our shape here, got our axes, although I think I accidentally cut off the x-axis label, y-axis, there we go. So let's start by breaking this up into a couple shapes. So I figure probably the easiest way to go about things would just be three shapes here. So we got this line here and a line here. So that'll give us this thing and this thing. Wait, I want a red. There we go, red. Or actually it's fuchsia. Whatever, fuchsia. Okay. So we'll just follow along with the kind of same process that we had before. We'll keep the reference system this time because it doesn't look like it'd be any particularly all that much easier. So let's see here. Let us start by finding the moment of inertia for that triangle. So, sorry, rectangle, the rectangle in the middle. So what we can do, actually let's first start by finding the areas. I think that's an easy place to start off. Got our A1, that's going to be equal to 54 millimeters times, what do we got here? 54 plus 72 millimeters. $126 millimeters. Okay, so that's the area for that one. Next up, let's go for our top one there. So A2, 3, oh wait, no, sorry, that was 1, and our green's going to be 3. So A2, so that's 126 times 30 divided by 2. And again, it's all millimeters. So that gives us 1890 millimeters squared. And similarly, our A3 is equal to 72 millimeters times 48 millimeters divided by 2. $17.28. Add them all together. And we get 10,422 millimeters squared. So that's simple enough. Okay, so now to start adding up the moment contributions there. So we'll start with our 1, our fuchsia section there. So we're starting off here. Our x bar 1A1 is going to be equal to So the x bar is just the distance along the x-axis to the centroid. Or the distance from the y-axis. If you're looking at this in this plane here, so along the x-axis. So we know that the centroid of a rectangle is going to be smack dab in the middle of the rectangle. So we got 70. We got the 126 from here to here, divided by 2, which means that it's going to be 63 millimeters from either side. So the easiest way to get us a value here is just from 72 minus our 63. That gives us an x bar of 9 millimeters. And then our A1 we know from up here. So I'm actually just going to plug that straight in. 6804 millimeters squared, which is 61.2 thousand. Next up, same deal, but the y-axis. So again, we're looking for the location on the y-axis that the centroid's at, or we could also look at that as the distance from the x-axis. So that'll just be the 52 divided by 2, because the base of this rectangle is on the x-axis. So 52.2 divided by 2. Sorry, why did I say 52.2? The 54 millimeters divided by 2. Swear to God, I hate saying numbers out loud. I always screw them up. Anyhow, 27 millimeters. Again, times our value there. So that gives us 183.7 thousand millimeters cubed. Alright, so something similar for our 2 section here. We got our x bar 2a2. That's going to be equal to, what do we got here? So basically we know that the x bar is going to be located either 1/3 of the way from this end, or 2/3 of the way from this end. Either way works. So the base is 126 millimeters. 1/3 of that is 42. So that's 42. So then we can just get the distance from here to here to respect our coordinate system by taking our 72, subtracting 42, which gives us 30. So our x bar is 30 millimeters, and then our area is 1890 millimeters squared. And that gives us 13.7 thousand. Oh wait. No, sorry, I mispunched in my calculator. 30 times 1890. There we go. 56.7 thousand millimeters cubed. Same deal for ybar. So there, we're going to be working at 1/3 of the way up this base. So the base is 30 millimeters, so our ybar is going to be the 10 millimeters from the base up to here, plus the 54 millimeters from there to there, so 64 millimeters. And that is times our 1090 millimeters squared. 64 times 1890. And that gives us, rounding up, that gives us 121,000 millimeters cubed. Next up, we got our green triangle here. So the X bar 3A3. So that one, we can start from the origin and work our way over here. So that'll be 2/3 of this base distance here, since we're starting from the pointy end and going towards the base and not the other way around. So 72 times 2/3 is 48. So 48 millimeters times, what do we got for size here? 1728 millimeters squared. And that's given us 82.9 times 10 to the 3 millimeters cubed. And next our ybar. Is similar, but we're starting from the base and working our way towards the pointy end. So it's only 1/3 of the way down there. So 48 divided by 3 gives us 16. But in this instance, you'll note we're starting from the origin and going down. So we need to respect the sign conventions there too. That's minus 16 millimeters times the area. So minus 27.6 times 10 to the 3 millimeters cubed. All right, so and then essentially, if we want to find out what our X bar is, that's just going to be equal to the sum of our of our little X bar in area contributions divided by the sum of the area. So, well, let's do that directly. So we got the 61.2 plus 56.7 plus 82.9. That's all times 10 to the 3 millimeters cubed. And then we just divide that by the total area. So the total area is 10,422. Millimeters squared. Now cancel that out. That cancels out all but one of the millimeters. So the result we're going to get is going to be in millimeters, which is exactly what we expect. So anyways, What does that work out to? Okay. Times 1000 divided by 1044, blah blah, 10,422 gives us 19.3 millimeters for our X bar. So we're looking at, I guess, I don't know, what are we looking at? Probably somewhere around here. Something like that. Not, that looks reasonable, I'd say. And then we just do the same thing for our Y bar. Okay, I'll make it obvious this is a capital Y. Sum of our I bars, AI, divided by the sum of the IA, not AI. Sorry about that. Yeah, so just add those up. So our first one from the A term is 183.7. 183.7 and 121 and negative 27.6, and then those were all in times 10 to the 3 millimeters cubed. And then divide that by our area again. Alright, unit still cancels out to millimeters. So, plug that into the old calculator. That gives us a Y bar of 26.6 millimeters. So I guess we're looking at slightly above halfway through this little rectangle thing, so about here. So we're looking kind of like that for our centroid, which again I think all looks pretty reasonable. If you asked me to kind of point it out, I think I probably would have gotten within at least 5 millimeters of that point if you had to just guess. But again, we're in engineering, so we try to avoid guesswork if we can. Although at the very least, you should get a good intuitive sense of what your answer is. I mean, because if you had done your calculations and you actually found it to be over here, well, guess what? That's probably a pretty good sign that you should maybe revisit your calculations. Yeah, you might have screwed up along the way. So that'll be that for this question.